In the last video, we were talking about stability of equilibrium solution of a differential equation, of an autonomous differential equation, right? So if y star is an equilibrium point of dy over dt equals to fy. So this equation is first order, okay, not autonomous differential equation, right? We say that y star is asymptotically stable if any solutions that started close to y star approach to y star in the long run. That is, limit t tends to infinity, y equals to y star. If that is the case, then we call asymptotically stable. Otherwise, we call unstable, okay? So there is a case of semi-stable, okay? In the higher dimension, if there are more than one equations, we call saddle or whatever. We will discuss that later, but for now we just call semi-stable, okay? So from one side approaching to the equilibrium solution, from other side not approaching, going away, okay? We'll see on this example all these type of equilibrium points, okay? Let us see the last example for this testing the equilibrium, finding the equilibrium solution and testing the stability. So here, check the stability of dy over dt equals to y squared minus 1. This is autonomous because there is no t on the right side, right? And where y sub 0, that is the initial value, initial value of the solution is anywhere between negative infinity and positive infinity. Anything is possible there, right? So first of all, how do I find the equilibrium points? Is you do 0 for dy over dt, right? So how do you do that? Is you do dy over dt equals to 0, implies you get y squared times y squared minus 1 equals to 0, right? So what do you get? If you set the first factor equals to 0, then you get y equals to 0, and then if you do the second factor equals to 0, you'll get y squared equals to 1, right? So that means y equals to plus and minus 1. That's what you get, right? These are the equilibrium points. Now to test the stability, what we do is, first of all, we need to plot them. We need to draw the phase portrait or the phase line or the phase plane, whatever you say, okay? Usually for the only one equation we call phase line, okay? So for the phase line, what you do is you draw a horizontal line. This is a horizontal line where y is there. And then what you do is there is a vertical line where is y prime. That's the dy over dt, right? And mark those points, those equilibrium solutions on the horizontal line. So let's say this is negative 1, okay? Let's say this is 0, and then this is, let's say, positive 1, right? Now what we want to do is we want to find the sign of y prime on each side of these equilibrium points, okay? So how many intervals are there? There is one interval is y is less than negative 1, another is negative 1 is less than y is less than 0, 0 is less than y is less than 1, and y greater than 1. These are the intervals, right? Now what we do is we want to find out the sign of y prime in each of these p's, okay? So what we do, you pick a test point here, let's say negative 2 as a test point, and plug in that into this equation, okay, or in this right hand side, and then check the sign of y prime. So if you plug in negative 2, you get negative 2 square is positive 4 times negative 2 square is positive 4 minus 1 is 3. So 4 times 3 is 12, right? So that is positive. So this is positive, means what we do, let me use different color there. This is positive. That's what you do. So let us plug in another test point from this piece. Let's plug in negative 0.5, okay? If you plug in negative 0.5 here, you will get positive 0.25 for y square, and positive 0.25 minus 1, that will be negative 0.75, right? And then times that will be negative. So negative means you turn that arrow on the left, right? Similarly, between 0 and 1, you get negative 2. So you get that arrow turning left, and then for so it is less than 0, y prime is less than 0, and the last one, if you take a test point somewhere here, then you will get let's say 2, right? You get 2 squared times 2 squared minus 1. It's again positive, so you will see that goes that way. All right. So what we are going to do next is we want to draw a graph for y, not y prime, y versus t, right? So what are the equilibrium solutions? 0, positive 1 and negative 1. 0 is this one. Let's say this is 0, y equals to 0. Y equals to positive 1 is here, 1, and y equals to negative 1 is somewhere here. So we always draw horizontal line for the equilibrium solutions there, right? Now what we need to do next is, so based on this, I mean, you can see from here which one is stable and which one is not stable, right? So you see that this point is stable because from both sides, the arrow is turning on that point, right? So this is stable. This is unstable because from both sides, the arrow is turning away from this. This one side it is getting into that, the other side is getting out of that. So it is called semi-stable, right? It is actually unstable. We call semi-stable there. So what we do is we are going to draw the lines from here, because what we do is if it is stable, then if you draw a line close to that point, okay, then all those solution curves, if you draw a solution curve close to that equilibrium solution, then the solution curve will get close to that. Otherwise it is unstable, right? Let's say at positive 1, on the bigger value of positive 1, it is going away, right? So it is like that, right? Like this. If you take a point, or if you start a solution close to that point, then the solution is going away. Similarly, below 1, between 0 and 1 is going away too. It is negative, so it should be decreasing. Above 1, it is increasing. This one is increasing, so that's why we wrote increasing curve. Below 1, between 0 and 1, it is decreasing. So that's what you do, right? You see that? Now, between negative 1 and 0, it is decreasing too. So it is again decreasing. You see that? And then below negative 1, it is increasing, meaning it is going like this. You see that? When time is bigger and bigger, you see that the solution curves are not approaching to this line. They are going away from this line. They are going to this line. So it is stable, right? This is unstable. So this is also unstable. We call semi-stable because it is going, one side it is going into that line, and then on the other side it is going away, right? So it is semi-stable. So this is how we determine the stability, ordinary differential equation that is autonomous. Okay, so first order autonomous differential equation. This is how we find the stability, equilibrium, and determine the stability. So the next thing we want to do is we want to find another technique to check the stability. Actually, this does not depend on the graph most of the time. Sometimes you may have to draw the graph, but on this method, you just use the derivative to find out the stability of equilibrium points. Okay, so we call linearization technique. Okay, so what we do here is we check the sign of, if you have, let's say, autonomous equation dy over dt. This is first order autonomous equation f of y. If you have this, and then the equilibrium point, suppose equilibrium point is y equals to y star. So if you want to test the stability of this equilibrium point, okay, you don't have to draw the graph. So what you need to do is, what we do is you find out the derivative of the right side function. You find out f prime, and then replace y by y star, and then check the sign of f prime y star. If it is positive, then y star is unstable. If f prime of y star is negative, then the equilibrium point y star is stable. Okay, and then if f prime of y star is equals to 0, then inconclusive. Meaning you will have to draw the graph in that case. Okay, guys. All right. So let me write down the statement of the theorem that tells this, and then I will do this example by this technique. Okay, guys. All right. So let me write the theorem that says this linearization technique. Theorem. Let y star be an equilibrium point or solution of the autonomous ODE dy over dt equals to f of y, and assume that f of y has a continuous, let me write continuous in short, continuous derivative, let me write the derivative in short, in a vicinity of y star, in a vicinity, in the close neighborhood, that's what it means, of y star. Then if number I, f prime of y star is negative, then y star is asymptotically stable. Number double I, if f prime of y star is positive, then y star is unstable. And if f prime of y star is equals to 0, then no information about y star. So we'll have to do these graphical techniques to figure out whether it is stable or unstable or semi-stable in that case. Okay, so let us do one example here. Example, find equilibria. Oh, by the way, so the plural of equilibrium is we call equilibria of dy, exactly the same example, dy over dt equals to y square times y square minus 1 with negative infinity is less than y0 less than infinity, and determine the stability. Okay, guys, look at this. What is f of y? This right hand side is f of y because it says the differential equation is dy over dt equals to f of y, right? So here, so let's write down the solution. Okay, so what are the what is f of y? F of y is y squared times y minus 1. What is that? That means y to the 4 minus y squared, right? So what are the equilibrium points? Equilibrium points are y equals to 0, 1 and negative 1, right? We did that already. We found that already here, right? Just set that right side equals to 0 and solve for y. Now what is f prime of y? We need to find out the first derivative of that. You will get 4y square minus 2y, right? Now we'll plug in that 0, 1 and negative 1 for f prime of y. So what do you get? F prime of 0 is what? 0, right? So inconclusive. F prime, let's plug in 1. You get what? 4 times 1 minus 2 times 1 is 2, which is positive. So unstable. What is unstable? Unstable is that equilibrium is unstable. This 0 is inconclusive, but we know that 0 is semi-stable. We found that already. Y equals to 0 is semi-stable there, right? So f prime of 1, because this method, this linearization technique was not able to tell anything about that at y equals to 0. But at y equals to 1, it is unstable. So this equilibrium point is unstable. Y equals to 1 is unstable. So how about f prime at -1 equals to, plug in -1 here. 4 times -1 square is, oh, by the way, this is cubed, right? I'm sorry, this is cubed. So 4y cubed minus 2y. At 0, it is 0. At 1, it is 4 times 1 minus 2. That is 2 positive. Now, at -1, you get -4 because 4 times -1 to the cubed is -4 minus 2 times -1 is positive 2. So that will be -4 plus 2. That is -2, which is less than 0. So it's stable. So you can use this linearization technique to determine which equilibrium point is stable and unstable. Again, as I said, this method may be inconclusive sometimes, and you may have to do the graphical technique again, but most of the time it will give you the stability of the equilibrium points. Thank you, guys.